Hi, starting out with Chapter 17 lecture, Aqueous Equilibria. It's really a continuation of acids and bases and equilibrium. So the first thing we'll talk about is the common ion effect and its relationship to Le Chatelier's principle. So if we have an aqueous solution of acetic acid, which is a weak acid, we know that there is an equilibrium between the molecular form of the acid and the hydronium ion and the acetate ion. So if acetate ion is added to the solution, let's say in the form of sodium salt, NaC2H3O, that's sodium O2. That's sodium acetate. So sodium acetate, because it's salt, when placed in water or in a solution, it will completely ionize into the sodium ion and the acetate ion. So what I'm doing effectively is increasing the concentration of the acetate ion by adding that sodium acetate salt. So when I do that, I'm adding a common ion. And so the common ion effect, according to Le Chatelier's principle, is that the equilibrium will shift to the opposite side because there's a stress applied here, and that will cause actually a decrease in the ionization of that acetic acid. So the common ion effect is the extent of ionization of a weak electrolyte that is decreased by adding a strong electrolyte to the solution that has a common ion with the weak electrolyte. So the acetic acid is the weak electrolyte. It breaks up into these two ions, hydronium and acetate. And then when I add the strong electrolyte, which is the sodium acetate, strong electrolyte, single arrow, everything breaks up into these two ions. So now these two ions put stress on the system and shift the equilibrium back the other way. So what we want to look at this quantitatively and how we calculate pH when this common ion is added. So the example would be to calculate the fluoride ion concentration and the pH of a solution that's 0.2 molar HF and 0.1 molar HCl. So here's what we do. When we take the HF, it's a weak acid, hydrofluoric acid. It's going to react with the water to produce the hydronium ion. That's supposed to be an H3O, hydronium ion, and the fluoride ion. So we know that the equilibrium expression, or the Ka expression for this weak acid, is hydronium ion times the fluoride. So my two products over my one reactant. That's my expression. So in order to find out how things change, in order for it to reestablish its equilibrium when an extra fluoride is added to the solution, then, I'm sorry, not an extra fluoride, when extra hydrogen is added to the solution, how will things change? So here's what I know, that I have I start out with 0.2 molar HF, that's given here. 0.2 molar HF is given. And I also know that I start out with 0.1 molar HCl. So here's what it would look like in the ice table. I have the 0.2 of this. I have none of the F, but in problem like this that we did in the last chapter, chapter 16, we would have also called this 0. But now that we've added the hydrochloric acid to it, and that's a strong electrolyte, I'm going to have plenty of this hydrogen ion that's going to have an impact on the way the equilibrium establishes itself. So I include that 0.1, which comes from here, because that's the molarity of the solution. That's a strong electrolyte that I added. And remember, we can just use hydronium ion and hydrogen ion interchangeably. They're effectively the same thing. H3O positive. Okay, so now I have my ice table set up. And so what I know is that because of the ionization that the weak acid is going to undergo, I know that this side is going to go up by x, is going to go up by 1x. This is also going to go up by 1x. But I essentially have a good amount of that hydronium ion here. So it's 0.1 plus x essentially is going to equal 0.1. I don't really know what that x is, but I'm going to find out. But I do know that the amount that I get from the ionization of my weak acid here is minuscule. So I'm going to ignore it and just say that I effectively have 0.1 of the hydronium ion. So now I'm going to say 0.2 minus x, okay, which we have said is not very significant. We're just going to call it 0.2. We're going to call the hydronium ion 0.1, and now we're going to figure out what the fluoride ion is. So once I calculate my, I use my Ka, I plug in the values that I know. I have my 0.1 that I plug in here. I have my 0.2 that I plug into my expression here. And then I can solve for my x. So then once I find out what my x is, that's going to be my fluoride ion, because right here in my formula, that x is synonymous with that fluoride ion. So once I find my fluoride ion, then what I can say is, all right, now I know that this x has a value. It's 1.4 times 10 to the negative third. So then what I do is I go down here and I say my hydronium ion was originally 0.1 because of the strong acid. Now I can add that x to it. You can say 0.1 plus 1.4 times 10 to the negative third gives me my hydronium ion concentration. It's not much more than the 0.1, but when you do a pH calculation, if you had to carry it out to 3 or 4 significant figures, it might make a difference. So if I take my pH formula, say pH is equal to the negative log of 0.1014, and I get a pH of roughly 1, which I would have gotten if I just used that 0.1 from my HCl. But like I said, you'd have to do watch for significant figures, because you really would need to show 4 sig figs in your pH.